1. How about the K? Now, the K value also increased, right? Okay, so, and this is K. And now it's 30% ACN. So how about separation? Kind of, right? We say now when K equal to 10, seems like they can be separated. Okay, but do they really achieve a good separation? Do you like it? Not really, right? Okay, so what happened? We see that 1 and 3. So this one, obviously, the selectivity factor, the alpha value for these two peaks, 1 and 2, are not good enough, to resolve them. These two, like, totally, say, co-eluted. And then what we need to do is say, okay, now the K value seems okay. Seems like, say, about within 7 minutes, the peaks can be separated. That's enough for that separation. But now the alpha, not good. So because there are two components, they cannot be separated from each other. Okay. So then our idea is, okay, so how can we improve this selectivity factor? Actually, in many cases, adjusting K to a suitable level, about 10, is all that is needed to give a satisfactory separation. However, so like in the case we just talked about in our figure B, so two bands still overlap. So pick 1 and 3, they still overlap. So, and that's why the selectivity factor alpha for these two species, for 1, 3, not good. They must be made larger. So, and how can we make selectivity larger? The most convenient way, again, is to change the chemical nature of the mobile phase while holding the predetermined value K more or less the same. What does that mean? That means what? We will keep K equal to 10 because we are satisfied with the separation time. Say it's good enough, okay? I think we have separated, but we're just not happy with the alpha value. So we keep the K the same, but we change the chemical nature of the mobile phase. You may ask me, what do you mean, the who? You say like change the chemical nature of mobile phase. I have changed. You see that I've increased the percentage of water from 59 to 70%, right? So I did that. So how can I keep changing it while keep the K the same? You just mentioned about if we change that, and then the P value change and the K value definitely change, and they cannot keep K the constant one. Okay, don't worry. Remember that, okay, for the most of the reverse phase chromatography, we have water. At the same time, we have organic modifier. But this organic modifier is not necessarily just be ACN, right? We have other choices. You can change this organic modifier to methanol. You can change it as a propanol. You can change it to acetone. You can change it to THF. You can even using a combination of just more than one organic modifier, right? So what we mean here is, like, say, by changing the chemical nature, we keep K the same. That means we are going to change the organic modifier in this mobile phase. Okay, but how? Which one should I know? And then, but what kind of rule can I follow? Okay, so here, the most widely accepted approach for this type of mobile phase optimization, we say, like, say, adjusting alpha, okay? So it's called the solvent selectivity triangle. So here, the mobile phase effects contributing to the selectivity are considered to be the result of proton donor, proton acceptor, and dipolar interactions. Okay, what are they? So for reverse phase chromatography, so the three solvent modifier, organic modifier, that correspond to these three is methanol. Methanol is proton donor. We say it's polar. Why? OH. This one is the donor, okay? Proton donor. And ACN. ACN is what? Is proton acceptor. It cannot contribute CN, but it can accept proton. And then tetrahydrofuran, THF, is considered as a dipolar interactions. So this are the three solvents, basic solvents. We use that in this solvent selectivity triangle for the reverse phase. So they correspond these three kinds of organic modifier. And in reverse phase, water is used to adjust the solvent strength of the mixtures and yield a suitable K. So that means water is there, always there. And it will be the combination of water plus organic modifier, and can be just one organic modifier, or can be more than one. Okay, so that's reverse phase. And these three organic modifier we are normally thinking about: methanol, acetonitrile, THF. Okay, and water always there. How about normal phase separation? So a similar solvent triangle is used. So, but the selectivity solvent are alkyl ether, methylene. This is corresponding to the proton donor, and methylene chloride, which is proton acceptor, and chloroform. Chloroform is the dipole interactions. Okay, so and the solvent strength adjustment is made by N-hexane. Okay, so things like reverse phase kind of is most widely used. So we will focus on the reverse phase. We're going to use this one as the example just show to illustrate how we can do a systematic mobile phase optimization using this solvent selectivity triangle. Okay, but here again, I want to say we use a simplified system. We just assume like this is we're just using an isocratic mobile phase. That means we're not using a gradient, not changing. But concept, idea is about same. So once you understand, so how and why would you this want to change the mobile phase, and then later on, even you're running the gradient, you still have some concept idea about so what you need to do, so how you can improve the separation, right? Okay, so based on that one, now let's go back to this example again. You see, we have just C. So the example we are talking about A and B, right? Okay, so we see this one, we say this is separation not good at very beginning, even case not good. And then we change the composition of the mobile phase, increase the percentage of the water. Now we can achieve enough separation, but not really good selectivity of component 1, 3. And the next step, this one is improve K. And start from here, we are going to work on how to improve the alpha. Okay, so again, so these are 6 steroids. Okay, compound 1, 2, 3, 4, 5. That's their name. And then the K value corresponds to peak number 6. We are talking about the K value number 6 because it's the last one to come out. And this is the reverse phase column. And then so using UV detector. Okay, so let's see what happened. Now, the next step, as we talk about, you can using water is always there. Then we change what? We change from ACN to methanol. Now we change ACN to methanol and see what happened. And we keep the K about the same. But then, however, so and it seems like the separation still not really that good, right? Okay, 4, 5, 6, they're very good. But still 1, 2 is not really totally separated. So can we like think about other ways? Can we do a, you see here, it's not really still not separated. So, and then how about we change to another one? The next one is THF, right? So try to change to THF. And then again, K is the same, just different combination with that 79% of water and 21% of THF. But still we say 1, 2, 3, 5, 6, 4. And then the problem become pick 4 and pick 6. Okay, so still not good. And then because now you have to try the single combination of water plus organic modifier, water plus ACN, water plus Here's water plus ACN, water plus methanol, and water plus THF. Okay, so if it's just single organomodifier, doesn't work. And then you may try several other experiments, additional experiment involving this one systematic variation. So, and then eventually it found that if we're using 77% of water, 12% THF, and 11% of ACN, and then it seems the peak can be well separated. Okay, you notice that when you're actually changing the solvent, and then the elution order can change, right? Because you're changing from the proton donor to something like, say, proton acceptor and so on. So this is pretty normal. When you are changing the organomodifier, elution order of certain compound may change, okay? And another thing is, like, say, later on we can talk about a little bit more. You see, when you're changing to methanol, you see, like in this case, if you look at the PI value, if you put polarity index, what is polarity index of methanol? 5.1, right? The polarity index of ACN is 5.8, okay? So, and then it seems like, say, methanol should be less polar, and then it's supposed to be more powerful, okay, to elute things out. And then so that means, like, say, you think about, probably we should, when we have the same K value, and then probably should say, not really, just a little bit less of ACN less than methanol. Not should be like, just like here, it's just 30%, if 49%, because if you calculate the p-value, and then for this combination, the p-value is about 7.7, like that one, if you can calculate it by yourself. Here the p-value, what I calculate, p1 equal to 8.88. And here it's just like about p equal to 7.7. You think about, if you just look at p-value, I should have a changed k. So why is that? Okay, so it's just something like, say, you should know is when the fraction of ACN and the methanol, so in this like solvent mobile phase mixture, is like not that high, say less than 50%. And then ACN is considered as a stronger, so solute, okay, stronger mobile phase than the methanol. So that means, like, say, it has higher elution strength. So in this reverse phase, ACN. So, and when it can using like much smaller fraction, so than what we calculated to achieve that, okay, separation. Anyway, so this is just something like probably extra, but when you are adjusting that, so in a real case, so you will see that. Well, anyway, so now let's see. So how did we start from this solvent selection selectivity triangle? So this one, this is a triangle. Look at this 3 light blue circles, okay? So this light 3 blue circles, they are the 3 binary solvent compositions that defines this vertex of the solvent triangle. So what is 100% T? T is actually a binary solvent. That means what? That means THF and water. And what is that M? M is what? So methanol and water, okay? Methanol and water. And what is A? A means what? A means ACN, you already know that, and water. So I mean, like, say, what does that mean? 100% of them? That means 100% of like mixture, but how can I know in this mixture how many ACN, how many water? Well, this is the combination, the mobile phase composition that you can use to achieve that K equal to 10 in your previous round, okay? That means for each of the real case, you have your own TAM, so that composition. Like for this case, for this particularly the example we're talking about, can anyone tell me, So what is the composition of T? Can anyone tell me? So what is percentage of water? What is percentage of THF in T? 100% T means what? 100% T means what? Do you know that? Can anyone like response in the chat box? 100% means this one. Means like say 79% water and 21% of THF. Understand? So this is the mobile phase composition, like you already optimized that for you to get K equal to 10. And how about 100% of methanol and water? Put 100% M in that triangle vertex. Corresponds to what? Corresponds to this one. Okay, that means so 51% of water and 49% of methanol. Understand? And then so this is 100% A. So that means here means A is what just talk about. So this is 21%, THF 79% so of water, and ACN. So this is 30% of ACN and 70% of water. And this one is 49% of methanol and so 51% of water. You see that? So that presents the three, so kind of this vertex, okay? And then that means you try. So the three binary phase first, solvent phase first. So water plus one organic modifier to see whether you can achieve a good separation, a good K and good alpha. If not, and then try the red dots. So what are those red dots? The red dots means so the binary mobile phase is created by combining equal volume of the blue dots. Okay, so that means we're using 50% of this mixture plus 50% of this mixture, A mixture, and then we got this red dot. So that will be the one that you're going to try next step. Understand? So that means actually this will be what if we plus it 120. So that will be 60%. The next step for you can do 60% of water and for this dot. So particularly for this dot, I would say 60% of water, and then so 15% of ACN and 25% methanol. So you can try this one for this dot. And then if not work, and you can try this dot. Of course, you can start from T or whatever. That's just if I start here. And then I try this one, and this one will be so 50% of this mixture and 50% of mixture, this one. So, and that will be about 75% of water, and try this combination. And so 10%. Yeah, very good. Yeah, THF, thanks for the response. So, and so 15% of ACN. Okay, okay, see that? 15% ACN. Understand now? If understand, can say okay to me. So because some student got confused here. So previous, okay? Understand now, right? Okay, very good. Very good. Thank you. Thank you for the response. So here, so it's just a combination of the other, right? Oops. Frozen here. My pen don't work. Oops. What happened? Oh. No. Sorry. You still see my screen? It's just jumped to another one. So can you still see the PPT, the screen here? Can you? Yes or no? Yes, okay, thank you. Very good. Okay, so and then so that means that now you try. If you're lucky, actually, if you're lucky, so in most circumstances, like say the 3 light blue one, it's pretty enough for you to get a good result. So if you're not really that lucky, and then so maybe one of the red dots already allowed to do so. Okay, so and for our case here, you can see that this one is very close. The results, you can see the figure E. This one, it has 77% water, 12% of THF, and 11% of ACN. That is actually very close to this dot combination. Understand? So now achieve it. So and then so if even the red dot doesn't work, so and then you can even try a ternary mobile phase show and this navy blue one. So that means so you contain 33.3% of N mixture, and then another portion T mixture and A mixture. That's it. So and usually 7 to 10 experiments not enough to define the solvent composition, so that can produce the best activity for a suitable K value. Okay, so you can see here is what we get. So you can see that this is different combination and show approximately equal solvent strengths. So this is say percent methanol in water. Okay, percent ACN, percent THF. Okay, so you can see here when it's more than 50, the difference is not that huge. Okay, so you can see ACN actually is pretty say the elution strength is pretty good. And for this one, the partition chromatography, we can see it has pretty wide application. So it can be used in pharmaceutical analysis to analyze the antibiotics, and then so steroids we just mentioned about, biochemical system to amino acids, protein, carbohydrates, lipids, food. So can analyze the artificial sweeteners, antioxidants, and so on. And then so even can so also very common for the pesticides, all this kind of analysis. And here just show some typical applications for that in the food analysis. Like the A is the soft drink additive. So and this one is polar, so nitrile colon, and you can see analyze the vitamin C ascorbic acid, so caffeine, sodium benzoate, and then the separation for that one. And this one is the organophosphate, so the insecticide is using again. So this is using CH colon, so this is reverse phase. And then you can see the separation and so on. So I'll just give some idea. But I think the best one is for us to have a very detailed example. And then so I like to using the Mellekant green, this one, determination of Mellekant green and leucomelon green in aquatic animals as example to show you guys as I mentioned. We start from the chemical structures of the compound, and then we think about the whole procedure. We think about the mobile phase, of course. We think about so the detector. We even think about how we can do the sample extraction. Okay, so let's do some practice together. So this is the Mellekant green, this one. So it's green, okay? It's actually a part of the green crystal, and it's also called the basic green 4 or Victoria green B. So it's a toxic dye. So it's toxic. Why you have to use it? Because when it's diluted, it can be used to treat fungi infection and bacterial infection in fish and fish eggs. So that's why. So and when people is transporting those fish like from one place to the other, so they add a diluted Mellekant green. It's just to like to control that one. So to treat that fungal infection. But it may cause the liver tumor formation in humans, so that's why it's forbidden. And it's the first found, like say 1992, detected in Canada, but then in 2005, people even found that in the seafood in Hong Kong. So and And for that one, so metacon green, so this is this one. So it has this structure. So the molecular weight is 329.4. And metacon green, actually, it has two major breakdown products. So which is carbonyl base. Because I'm base, so do you see the difference? Do you see the difference? You see that? A difference here. So it is acid base. So that one, so equilibrium product, metacon green. Basically, it's metacon green. So, and plus water. Because here you can see metacon green actually. So probably I first look at this one. For metacon green, okay, so it is charged, right? It is charged. Okay. So, and then do you think, so it's water soluble? Is it hydrophilic? Yes or no? Yeah. Now it has charge. Do you think it's hydrophilic? Do you think it's water soluble? Yes or no? Answer, you can probably like give your answer. I see your answer. Yes, yes, very good. Obvious, right? So it's charged. And then, so it's water soluble, it's hydrophilic. Okay, so metacon green, and then so it has acid base, equilibrium product with carbonyl base, and then so it can form the carbonyl and acid. So this carbonyl is just acid base one. But look at this one. And how about this one? Do you think like this compound, the carbonyl base, do you think it's hydrophilic or hydrophobic? What's your answer? Hydrophilic or hydrophobic? So it's hydrophilic or hydrophobic? A, hydrophilic, B, hydrophobic. So can you indicate your answer in the chat box? Hydrophilic or hydrophobic? B, hydrophobic, A, hydrophilic. Okay, thank you, very good. Okay, so it's hydrophobic, right? Okay, so you can see that now the charge is gone. So it's hydrophobic. So that means it's more lipid soluble. And then, so that's why. So when the carbonyl form, so it's like say produce like the breakdown of the metacon green. So it can migrate, it can spread across the cell membrane. Okay, so this one can across the cell membrane faster. When it is inside the cell, it is then metabolized into a form that's called leucometacon green. So this is a leucometacon green. Let's look at structure of leucometacon green and metacon green. So the one is, we say, it's kind of what reduced form, right? Okay, so it's the reduced form of metacon green. So it's have one hydrogen here. Okay, and of all these three compounds, only metacon green has color. So when it has color, what does that mean? When it has color, that means it can absorb visible light, right? Okay, so the other two does not have color, they're colorless. Why is that? Can anyone tell me? I'll probably say, look at the structure. So which one has a very big conjugated pi bond? Which one? Look at this one. Look at the metacon green, double bond, double bond, double bond, right? Here, conjugated, and then here conjugated, even so with the nitrogen here. So it has, because one of the electron already lose positive charge, and then so pi, you see that pi orbital here, 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 here. So like, so for metacon green, you can see it has a huge, a very large, so pi bond. So, and so it has the delocalized pi bond. So that's why we say that with more conjugation, the energy gap, I think this is why you should learn that from last semester, from pi to pi anti-bonding, right? Sorry. So because the gap between the pi and pi antibonding orbital. Pi antibonding orbital. So with more conjugation, so the gap between them become smaller. So when the electron jumping from pi bond to pi antibonding bond, so when it's more conjugation, the energy gap being smaller, that means it requires less energy for this transition to happen. So that's why. So they can absorb visible light to do so. Because compared with UV light, visible light has longer wavelengths and lower energy. Understand? So how about for this two? Here is no conjugation. It just has this pi, 3 separated pi here. So on each aromatic ring. So here is the same. So that's why only Melancon green, so it has color, but the other two does not have color, right? Okay. So now let me think about the detection. Now we're talking about LC. Of course, the thing about definitely we can use the liquid chromatography. How about detector? So for detector, obviously, for the Melancon green, we're using visible light, so which is 62 nanometer. But for this two, we can for using the UV, right? Or maybe think about because they have aromatic ring, recur. So what you have learned last semester when you learn a liquid spectroscopy. So are they good compound for fluorescence detection? Yes or no? So they have which chromophore? They have aromatic, right? Aromatic. So this one is a good one for fluorescence, okay? So that's why, so definitely, yes, very good, thank you. So this two can use, we can even use fluorescence for the detection, understand? So from chemical structure, that's what I mean. From chemical structure, now we have some idea. Okay, the thing is like actually when you are doing the analyzing of this Melancon green, you're not just like say analyzing Melancon green itself. Let me see. Wait, is that first? Why? Because like say I say like the Melancon green when it's carbonyl form that gets into the cell, and then once get into the cell, it metabolizes in the form of leucomelacon green. So it's found that it's the leucomelacon green, so they can persist in the fish tissue. None of the Melancon green so have degraded because the lifetime for Melancon green stay in the fish probably just 2.8 days, but for leucomelacon green can be much longer. So the leucomelacon green actually found to be the prevalent residue observed so inside the fish. So that's why when you're doing the analysis, we aim to measure both Melancon green and leucomelacon green. Okay, so now comes the issue. This one, hydrophilic. Okay, this one is hydrophilic, and this one is hydrophobic. It's hydrophobic. Okay, sorry. Oops, keep moving that. It's hydrophobic. Okay, so and then, so how can you do a good extraction of both of them? One is hydrophilic, one is hydrophobic. So and then it's not really that polar in polar solvent. And then what can we do? What can we do? Think about it. Maybe, so that means one easy way to do that is when you do the extraction, think about pH adjustment to see whether we can protonate this one. If you can protonate it, if you can give it, oops, I don't know why it keeps charging that. If it can give it one charge, that can make it more hydrophilic, right? Okay, more polar, right? Okay, so that means like, so probably think about when we are doing the extraction, we can using a relatively polar organic solvent because we want to extract Melancon green. And if we want to say extract the leucomelacon green at the same time, so probably in the organic solvent we want to add acidic buffer, And then so that can make the glucomannan grain so protonated and more soluble, more extractable in this polar organic solvent. Understand? Okay, so that is the way you think about. So after sample extraction, so we need to do the sample cleanup. If you look at structure of this glucomannan grain, of this one, if we have protonated, so can anyone tell me what kind of technique I can use to do the sample cleanup? Especially those who have taken the Monday courses, Monday course sample pretreatment. Can you answer this question? Very good, SPE. Which SPE? The different kinds, reverse phase, normal phase, ionic. What kind of SPE? What kind of SPE? Now it's charged, right? It's ion. And is this cation or anion? It's cation. So what kind of SPE we can use? We can use probably strong cation exchanger, right? Okay. So because of this one, so because it can be proton is charged, maybe after extraction, when we don't want to do the sample cleanup, we can think about a strong cation exchanger to do the sample cleanup, right? Okay, very good. And then so that means we load a sample, strong cation exchanger. So when you elute a sample, think about it. So do you want to using what kind of eluent? The mobile phase for elute for the SPE? Basic methanol or acidic methanol? Already forgot? That's okay. So we talk about later. Think about it. So because look at structure, we consider about the sample cleanup method we can use. And also because of structure, we think about, so when you load a sample, what the pH should be. When you elute a sample, what the pH should be for that to elute it out, okay? And then if you're using the LC, we'll see for LC, which column can we use? Even this one is like that one, but still can adjust pH. And then because of the aromatic ring here, probably we still can trust C18, right? But when we are using UV and visible, and also like can be UV and fluorescence, right? Can we use LCMS or LC tandem MS? Can we do that? Can we use it? Yes or no? Of course, yes, right? Of course, yes. And if you are using LCMS, if you're using ESI for ionization, now can answer my question. So which ionization mode can we use? Positive mode or negative mode? Will be ESI positive, ESI negative. Very good, thank you. ESI positive. Why? Look, right? Understand? Okay. And to facilitate the ESI ionization, we learned last week. And then maybe you're thinking about in the mobile phase, you want to add a little bit acidic buffer as well. To do what? Why I want to add a little bit acidic buffer? To help the glucomannan grain to be protonated in ESI. Remember we say the ESI, you prefer polar compound. So for glucomannan grain itself, it's not that polar. Okay, and then it may not be easily like say ionized. But if you add acidic buffer, like say formic acid, a little bit, and then that can help to make this glucomannan grain the protonation in ESI. Understand? Very good. So that is what I say. So this is the kind of practice. So we study from the chemical structure. Look at the chemical structure. Think about the chemical and physical property they have. And then starting from there, we can have some idea about what kind of solvent can use for extraction. And then so how we can improve the extraction efficiency. And then so after extraction, what kind of sample cleanup method we can use. If we're using SPE, what kind of SPE column we can use. Think about the condition for loading and elution. And then so and also like separation technique. So will that be more suitable in GC or LC? Okay, this one obviously LC better, right? So this one become metacongruent polar here, not really suitable for GC. So and if it's LC, what kind of detector can we have? And for this one, so obviously this one has color, like UV visible definitely work. And this one, so many aromatic rings, fluorescence can be a good choice. If you have LCMS, definitely even better. And then and because of this one's charged, and then so we think about ESI positive. Okay, so that's the whole idea. But we spent time talking about this one. So let me see what time. Yeah, and then so probably so we can take about 5 minutes. But before that, let me yeah. So I turn on my video. You see I'm wearing my N95 mask. The reason for that is actually my helper got positive, affected. So and then my child is having a fever. So I'm the only healthy adult in the family who can take care of her. So that's why. So I let her just sleep and do something by herself right now. So that's why today I cannot really teach until say 9:40 or 9:50. So and today I have to stop at 9. Okay. So today we just have 2 hours lecture because I really need to take care of the small ones. Okay. So thank you for understanding. So we take a 5 minutes break and we come back and then continue. Okay, so we'll start again. So first we see like extraction method can be the vertex or just like say sonication. So and first, so put the homogenized fish, so 1 gram, so into the container, and then so add 5 milliliter of acetyl nitrile, so relatively polar solvent, right? Okay, and then also acidic buffer. You can see now it had so this acidic buffer here, and also in the presence of antioxidants or enzyme inhibitor. Which one is the antioxidant here? Is hydroxyamine here. So hydroxyamine. So hydroxyamine. So this one. So it's try to help to prevent so the photo degradation of mitochondrion and leukomitochondrion, because both of them are found to be able to have the demethylation so under the light, and then vertex for 2 minutes. So here, so you can see in this method they had deuterated internal standard mitochondrion D5, leukomitochondrion D6. So if add this compound, if add this kind of internal standard, what does that mean? What does that mean? What indicate what kind of method, what kind of detector they're going to use? Can you give me some response? Mass, very good. So mass spectrometer, very good. So if using deuterated compound, isotope labeled internal standard. So that is for mass spectrometer. You don't use that for UV, you don't use that for fluorescence, okay? So because it's just like say replace hydrogen by deuterium. So that's D5, 5 hydrogen has been replaced. D6, 6 hydrogen has been replaced. So that would be original molecular weight plus 5. This will original molecular weight plus 6, right? So the reason to using this isotope labeled internal standard. So in mass spectrometer is to account, you see that it's at very beginning before the sample extraction, okay? Then it can monitor so the loss. So in the sample preparation, you can account for the ion suppression and matrix effect. So this one is very good because it has same structure as the analyte, your target compound, just like say the several hydrogen has been replaced by deuterium. Okay, so but its isotope label is expensive. Anyway, add in and then so do the vertex. Okay, and then so a different acidic buffer we say here using the ammonium acetate. So and it can using acetic acetate as well. So pH around 4.5, but can be the Mycvan buffer can use as well. The antioxidants. Okay, so it's this one. This one, the antioxidants. So this is the what shows for the Mycvan buffer. We use this one. So this buffer is mixture of 0.2 more per liter sodium hydrogen phosphate and 0.1 more of the citric acid. Okay, so we can see the buffer range. So the buffer range can be from pH of 3 to 8 if we're using different combination of fractions of this sodium hydrophosphate and citric acid. Okay, so if it's pH of 3, so that is about 20% of this sodium hydrophosphate with 79% of citric acid. So and if you pH equal to 6, so increase the level of sodium hydrophosphate to 63%. Okay, so this is just like say show you what is this buffer mean. And we say antioxidant is added to prevent the photo-oxidation degradation of mitochondria and leukomitochondria. So the mitochondria leukomitochondria, actually the two can kind of like say interchange to each other. So and because the leukomitochondria is the reduced form of the mitochondria, and mitochondria is oxidized form of the leukomitochondria. Okay, so and but they actually both of them they can be photo degraded, and what they're going to lose is the some mass spectrometer found that. So they may have the nitrogen demethylation reaction. So both mitochondria and leukomitochondria can able to use this method, so connect to the nitrogen. So that's why. So when you do the sample extraction, it's better to add some antioxidants. The one we just mentioned about hydroxyamine. So it's one often used. So another option is the TMPD. So that is often mentioned, this one. So, and ascorbic acid. So that's vitamin C. Okay, it's very good. So antioxidants. Okay. So, and if it has shown that addition of that TMPD or ascorbic acid to the sample, so they can largely reduce the degradation of both melatonin green and leucomelatonin green shell in all kinds of tissues. And also sometimes the non-oxidizing strong acid is added, because we're talking about extract the compound from the fish tissue. So they have lots of proteins, right? So it helps to release melatonin green out in a free form. So, and can be better get extracted. So, and this one, the PTSA, p-toluene sulfonic acid, is aromatic sulfonic acid. It is a pretty strong organic acid. And if we talk about this acidity, it's about 1,000,000 times stronger than benzoic acid. So, and it's one of the few strong acids that can that are in solid form, so that can be easily just weighted. Okay, so and the other choice is PSA, but this one is often used. So to denature the protein and to make melatonin green and leucomelatonin green will easily get extracted. Okay, so and then do sample cleanup, and because it's a kind, so that's why. So you can do liquid extraction, but what we do normally, so we do the SPE, and the SPE column we use strong cation exchanger because here. So that means now we are using the analyte isolation, right? So because we are going to retain what? We're going to retain the analyte, the compound, instead of like say just like retain those interference. Okay, so and you can see because we can use a strong cation, then it has sulfonic acid bounded. So that means in the stationary phase, because cation stationary phase is negatively charged. So it's like this one. Okay, minus here. That's what you show here. Yeah, you see, this is a strong cation exchanger. Okay, so it can retain. So the melatonin green or leucomelatonin green will be, that will be NH plus, right? So H plus do that one. Put it right this way. Leucomelatonin green. So and then can be retained. So by this, so ionic, electrostatic interaction is that electrostatic interaction. So retain that. So that means you have to make it charged to be retained. So and then when you want to release that, because the stationary phase is strong, so cation exchanger, so it's just remain charged over the whole pH range. So what you can do is say you have to neutralize the analyte to elute it out. So how can we neutralize this one? How can we make it neutralized? So at OH, right? Okay, so that means you can using a basic. You need to use a basic, so methanol to elute it out. Okay, to elute it out. And this is what we see here for strong cation SPE cartridge. And then so we often use the OSIS MCX is what we often use. We can using Merck SCX, and this is packing. So normally if I've got more mass packed, that means more the larger sample volume you can handle. Okay, normally the mass of solute is equivalent to 5% of the sorbent mass. That means if you have 5 milligram of the total solute, that means you need like say 100 milligram of the sorbent, depends on how much you handle. Okay, so then you choose the right SPE column to do that, and have to use 4 to 8 times of sorbent bed volume for elution. And then so the load speed normally is just like say we do like just let it go through drop by drop. So how will we do this one? So first you want to do some precondition. So the strong current exchanger SP can be preconditioned by a mixture of ACN and DCM. We're using the ACN to do the extraction, right? Okay, so if you use DCM to do liquid extraction, so then you want to do that one. But if not, just ACN should be fine. So after sample loading and to be washed by DI water, methanol, ACN, DCM to get rid of some of the interference. So we normally do that. Okay, so and then then you do elution. Do elution, we say using 2% of ammonium in methanol. We call that basic methanol. So why we're using methanol, we're not just using 2% ammonium. Why is that? Why is that? Because after sample elution from SPE, so still, if we want to get enough sensitivity, because it's trace amount, what we do is we will further pre-concentrate it. When you pre-concentrate, what do you mean is that we are going to blow the methanol. Okay, so we're going to say, and then even smaller volume. What we do is we're using the pure nitrogen gas, and then so we use that. For example, you elute it here. If you have a valve, you have say, if you elution, you got normally say 2 or 3, just say 2 milliliter, so of the basic methanol eluted. But still, like say, if you say still too much, I would still want to like pre-concentrate. I want to eventually make it to be about say 100 micrometer. What are we going to do? What we're going to do is that we normally have something, so I say the conic shape of the bottom, and then so you have it, so the pure nitrogen gas blow in, and then so here is the heated. So in the heating module, you can gently hit at 40 degrees C, and the nitrogen that goes through, and then the solvent then can concentrate. So you can even like say blow it dry, okay, but gently, and reconstitute in 100 microliter of the solvent. So same as the starting solvent mixture of your LC program. Okay, so this is how we do that. Okay, so this is for strong current exchanger. Remember, we adjust the pH to do that is because you want to charge for loading. You want it to be neutral for elution. Understand? So, and for determination, we're using liquid chromatography. Okay, so liquid chromatography and the column, C18 column. So, or can be phenyl hexane because it has aromatic ring. So, and then this column should be okay too. And mobile phase can using say, again, we say using the ACN and also acidic buffer and do that. And then so of course you can do the gradient, and acetate buffer can be the ammonium acetate or sodium acetate, and there's some injection volume for that. So and then just so 10 to 200 microliter should be enough. So and for detector, we also mentioned that we can using the UV visible, right? So and if you're using visible, then 620 nanometer. But say if you want to like say using the visible spectrometer to measure both of them, then no way for leucomelanocorrin, right? So and you have to do the conversion. But so in previous time, people also say convert leucomelanocorrin to melanocorrin, not just for the visible light detector. Even think about the mass spectrometer. So because the melanocorrin has the charge, so it's more polar, more easily analyzed in ESI. So and then so that's why. So to improve the sensitivity of leucomelanocorrin, the paper mentioned about, so they oxidize the leucomelanocorrin first to melanocorrin and then do the mass spectrometer analysis. But how to do that? So oxidation, you can do either pre-column or post-column oxidation. So you can using the lead oxide. So or this one is called the so DDQ, 2,3-dichloro, 5-dicylanol, and benzoquinol. So this one is for pre-colon. It's even like say before you add it to do the SPE, so you can add this one certain amount of DDQ into the sample. So before you do the SPE colon, okay, after extraction, and then let it react for 30 minutes, and then so can do the conversion. But well, I think this is really extra step. It costs the extra arrow things. So nowadays people won't do that. Okay, they just mention about some of the method mention about that one, some of the paper doing the analysis. And for lead oxide is for post colon, it's after separation. So you can let the one tube pass through the colon, and then before it get detected. But there has many drawback, you know, if you're using the one, so many of sample carryover could happen. And you can see metacon grain. So oxidized leucometacon to here is a reaction. You may oxidize then to other form, right? And also the lifetime so of this one is not long, so you have to replace the oxidation that tube or colon so from time to time. So let's just mention that. And then so a detector can be the fluorescence as well. So using the visible light to measure the metacon grain, but leucometacon grain fluorescence can be so excitation at 265 nanometer and emission at 360 nanometer. Okay, so fluorescence, we know that it have jump here and it have internal relaxation to a lower level of the excited state and jump back. So that's why. So the gap for excitation energy, so and it's larger than the gap for the emission. So that's why. So the emission wavelength is always longer than the excitation wavelength. Okay, and this one you're just directly using visible spectrometer, and then so the fluorescence detector that's directly to do the analysis and can be quite sensitive fluorescence as well. And lost possibility 10 ms. So LCMS. So we mentioned about why has to be ESI positive, right? Okay, and then to make it even more sensitive, so we can do the MRM mode, multiple reaction monitoring mode. So I guess like you guys have, if you have taken mass spectrometer last semester, so you should already know. So, and what does that mean? And for this one, so you basically you select you have first one, so you have some fragments, and then you select one to do the further fragmentation. So the precursor, so you have the mother ion and daughter ion, right? So at least 2 MRM transition has to be monitored. And then so we use the relative ion intensity of the diagnosed product ion. So, and we have 2 pairs, one for the more abundant one is used for quantification. And then the least abundant one, so the second abundant one, not least, the second abundant one is used for confirmation. Okay, so that's what I do for that one. So, and sometimes, as I mentioned, the post-colon oxidation is used to convert leucometacon grain to metacon grain, because the leucometacon grain from its chemical structure is non-polar, it's not charged. So, and then it's more difficult to get charged in ESI. So, and that's why. So that's why it has the post-colon oxidation. Okay, so, and this is how they monitored. You can see that for the metacon grain, so itself already positive. So that's why in ESI, it does not need to be protonated. Understand? So because itself already has the charge. Okay, so that's why the precursor ion, so it's the molecular weight, which is 329.1. So it can produce 2 pairs. Can produce, like say, the first one is 313. So that one. So the other one is, let me see, it's the 208. And this one is leucometacon grain. Leucometacon grain, now the precursor ion is N+1. Why? Because itself is not ionized. Itself is a neutral compound, so it's protonated. So in ESI, so that's why it's N plus 1. Okay, and then so it has the product ion, you see. And for the methyl green, if it's 313, that's a neutral loss of methane. And then so, and this one is 208 come from the neutral loss of this compound. So dimethyl For nucleomethyl green, so it's also, so one is for the loss of methyl radical, the other is just rearrangement and neutral loss of taurine. So anyway, so here you can modify the condition, okay? So can make it like say, so optimize that. So this is a collision voltage to have this one from the precursor ion to product ion. Okay, so you can see if it's just 20, so and from methyl green, you still see the majority, the big peak is just a precursor peak. So no fragmentation. So at this point, almost, right? And for nucleomethyl green, you can see here. So this is the precursor ion. It's a precursor ion. So for product ion, okay, so you can see some, but not so about. You can see the most about is this one. So that means this voltage, the collision voltage is too low, okay, not enough. So increases in the tandem MS to 30 evolts. And now you can see for methyl green, it start to have fragments. Okay? So, but still not good enough because the most dominant one is still itself, the precursor ion. So we want more daughter ion shows up. But however, for nucleomethyl green, you can see that now the precursor ion become very tiny, small, but still recognized one. And we see 2 daughter ion showing up here, become the most, and the most dominant one is 239.8, and the other one is 315.8, so 316. See, we say we need to monitor this too. So that means now the 30 evolts is good for the nucleomethyl green. This is condition we choose that. And obviously we use this ion for quantification or for what? Which one we use for quantification? The most abundant pair. So this 239. And then, oops, I don't know why I'm switching all the time. So, and then for this one, we do for confirmation to the ratio. Okay, and then so that means 30 evolts is good for nucleomethyl green. But how about for methyl green? 30 volts still not good because the precursor ion too abundant. And then we further adjust that. So increase to 40 volts. And now, so for the methyl green, you see more abundant for the daughter ions. And this one, 313.3 we use for quantification. And this one for confirmation. So that means 40 evolts for methyl green and 30 evolts for nucleomethyl green. So basically, this is what you do. So you can do that by direct infusion into the mass parts, and then you adjust the parameter. Okay. And also, some people did the stability analysis of the methyl green and nucleomethyl green. So they spike those both compound onto the fish fillet and put it in the freezer. So store it for 1 month, 2 months, and 6 months. And it seems like say methyl green, both methyl green and nucleomethyl green, they're quite stable. Right? You can see it's not just decay. The decay is not obviously, so it's about a 10% of the decay. So even after 6 months. So that means if it's safe at minus 20 degrees C, it could be stable. And how about at 4 degrees C? Let's try that for, excuse me, different days. 1 day, 2 days, 4 days. And but however, I mean, 4 degrees C, not good. So you can see this, even after 1 day, it just already 4 degrees C, already like dropped about 24%. And then So after 4 days, so in this refrigerator, so at 4 degrees C, already dropped to, like say, about 60%, like lose 40%. And this one, same. So 4 degrees C, not really good for storage. And then so they also try some freeze store. This one, the cycle, that means that the freeze and store it at 70 degrees C for 20 minutes. Okay, it's thinking about some frozen food, those kind of things, to see whether the treatment will make them decay. Okay, and it found like it does. Okay, if we do that one, so and that one, so that means like say actually the Malacan grain and liquid Malacan grain, they're not really thermostable. If I say when you do the analysis, you want to analyze right away, and if you really want to have to store it, and store at minus 20 degrees C, not 4 degrees C. Okay. And also they can do some degradation because of photo degradation. And then so both of them have been detected. You see, it's because the nitrogen demethylation products. And so that's why it's found like addition of the this one, so kind of the antioxidant, like the TMPD, hydroxyamine, so we talk about, or ascorbic acid to sample, could largely reduce this degradation. So in all the tissue, and then so and that make them to be better, to be like say reproducibility of the result could be better. Okay. So let me see. So now it's one of the case study I want to show you. So this is I get from this paper. So it's the confirmatory analysis of Malacan grain and liquid Malacan grain in LC tendon MS. So you can see they homogenize the sample, but you have to really mention when you do this kind of food sample analysis, is it with bone or with skin or something, okay? So, and then you spike the deuterated Malacan grain or liquid Malacan grain. We know that they're going to using mass spectrometer. Shake for 5 minutes and sonicate in 20 millimeter of ACN with the buffer solution, pH of 3 to make sure can be charged. Centrifuge, transfer the superlatent and do the re-extraction, and then centrifuge and combine. So that means extraction for 2 times. And then you can see already you got 40 milliliter of ACN. So, and then condition the SCX. And then it's a strong contact exchanger. So with methanol and ACN with the buffer, load the sample, wash that, and then elute by the basic methanol, what we mentioned already, in 3 portions, each time using 2 milliliter. So that means you have eventually 6 milliliter. So that's why you're not going to directly inject that one into HLCMS. You do further pre-concentration. So as I mentioned, blow it to dryness on the vacuum. This one is on the vacuum. We normally using that pure nitrogen gas at 40 or 45 degrees C, and reconstitute using ACN and water. That means in the HPLC method, so it's probably just using like this kind of things. Just ACN and water will be the mobile phase with ascorbic acid. So this one, a little bit of ascorbic acid for what? It's for antioxidant, to prevent your sample to have the photo oxidation. So that's why when you do the LC analysis, so you want to using the vial, you want to using the amber vial. Amber vial, what do I mean? That means the brown colored, not using the clear one, using the brown colored, not using that white transparent one, because it can also further prevent photo degradation, right? Okay, so this is something that you pay attention to make sure your experiment has very good reproducibility and then sensitivity. So this LC condition, we can take a look. So first, component A. The mobile phase A in LC analysis is often the aqueous phase, okay? So you can see here, the component mobile phase A is ammonium formate, okay, buffer plus, so water 95%. with 200 microliter of formic acid. Okay, and then B, this is aqueous phase. So this is aqueous phase, and then so this one is the organic phase. This one is ammonium formate buffer, because this one plus acetonitrile, sorry, ACN. ACN, so 95%, ACN 95%. Okay, and with 200 microliter of formic acid. So here I just want to mention one more thing. In the reverse phase, although we say a range of organic solvents are suitable for use, okay, so but actually only a few has been used by routine, okay. So we when we think about the organic phase, we think about, you say, oh, you just mentioned about the solvent selection triangle. Yeah, that's true. So actually in the reverse phase chromatography, you'll see that most of the time, so ACN or methanol, these are the two so that often used. Because when we think about the organic modifier, we think about some properties such as the miscibility with water. So they should be miscible, that means water miscibility should be good. And polarity, and even if you're using UV visible detector, you have to even think about UV cutoff, UV cutoff that wavelength, and also viscosity and so on. So we mentioned about something like, say, can be, say, isopropanol IPA, so that one can be used. But say for isopropanol, that one, it normally has and THF, you see that we mentioned that already, right? So they can provide pretty good the elution length, strength. But however, so for IPA, so isopropanol, its application is kind of limited because of its high viscosity. We don't want to use some solvent with very high viscosity because that can cause a high back pressure. And also, when the viscosity high, what is DM will be small, right? Okay, so and then so that way make some of the performance not really good. It influences C term, right? And for THF, what is the limitation for THF? You don't want to use too much THF, right? If you are using analysis to experiment using THF, John will be mad. Why? Because the THF is erosive. It can degrade pump seals. Okay, it's really bad. And then can, along with some of the PEEK tubing and fittings, and then they may block the system, cause very high pressure. So if we can have other choices, we try to say avoid it, but you can be careful. And acetone, which is inexpensive, and also have pretty okay elution property as acetonitrile. However, its UV absorbance limit, so make it to be limited in some application. And ACN has so many advantages, so that's why. If you say ACN or acetone, then still prefer ACN. Okay, so that is the thing to think about. And even ACN and methanol, they also have some comparison. And then for ACN, so even although the price of ACN is more expensive than methanol, but you can see that in many cases they use ACN, but methanol is also very popular, I have to say. So and because like say some advantage for ACN is like normally if you run ACN, so you can see for the whole system, so the kind of if they give the same flow rate, and then the pressure of the column if you're using ACN will be relatively lower. And also when you are using ACN, so the cutoff, UV cutoff, if you're using UV, the UV cutoff, the wavelength, I think it's 190, so which is the shorter than that of methanol. So that means if you have that one, so and then that's can have you make you so more sensitive or good for the short wavelength range. So that's why. So I just talk a little bit more about this issue about when you are choosing the organic modifier. Okay, so this is something that you think about. And then so and also you see that adding some formic acid, because we are focused LC part, right? So the reason for that one, I think all already know. So why add some formic acid? Now we're using ESI, right? Okay, so it's just like say It just helps it to be easily get analyzed, right? So ionized, so in ESI. So organic acid, this one is easy to evaporate. So this one is formic acid. So just add small portion, so as low as possible. The normally just result to about 0.1%. So easy to evaporate and can favor the ion production. So, and even had a high percentage of organic solvent. Okay, so, and this is good for that one. So that's why, so when you are thinking about the mobile phase in the LC-MS analysis, it's quite critical because it affects not only so the chromatography separation, but also the analyte ionization and sensitivity of mass spectrometer. Okay, so this is all the things you may think about. Okay, so that's why we adjust pH because we want the leucomelanocortin green to be charged, and also formic acid, so help for the ionization. So in the ESI part. But anyway, so let's take a look. So for this one, so now they have this transition. So and then so use the collision voltage. You can see they use different cleaving voltage. So and then so retention time. So pay attention to this retention time. This is also interesting for you to see. 8.1 for melanocortin green. Leucomelanocortin green, so 13.2. I also see that for these two internal standard, they comes out the same retention time as their so corresponding compound. So how can they be differentiated? You see, they co-elute. So how can you say which one is which? Remember, they have different what? Different molecular weight. Okay, so you can D5 melanocortin green. So that is 5 hydrogen replaced by deuterium. So that's why. So it's like 3, 3, 4. Okay, so and this one, so leucomelanocortin green, so it's also D5 here. It's 5 for the replace, so it's with 3, 3, 6. So the transition we look at if we're using mass spectrometer, you're looking at the M to Z ratio. You're monitoring the mass fragments. So that's why even though it comes out same retention time, fine. Okay, look at the mass fragments and take the ratio for do so. Okay, and this is a condition for mass spectrometer. And also, I say pay attention to retention time. Go back. Let's go back to the previous slide. Okay, condition 8.1. Remember 13.2. What is condition? Look at the table here. What is the mobile phase condition? It's always starting with high fraction of aqueous phase. Always start about 90%. This one, 90%. And then start to change to 50 to 50 A, 50% B at 3.0. And become 10% of A and 90% of B at 7.2. And this one will last from 7.2 minutes to 14.5 minutes. Why do so? Anyone can tell me why do so? You tend to be more organic phase, and then so what? And then it can help water and organic phase. Which one is less polar? Which one has high elution power for those non-polar, relatively non-polar species, less polar species? Organic phase, right? You're increasing the organic phase fraction because you want to elute those more tightly bonded to the colon, those compounds, to elute them out. You want to decrease the K value. You want to, it comes out. Okay. At the same time, we see that both melanocortin green and leucomelanocortin green, that comes out at high organic fraction. That's a good point for LC. Because in the LC-MS, you're using the ESI, right? ESI, remember, they got charged in liquid state. And then, so they have the solvent evaporation, right? So, and then, so melanocortin green, so for organic, for ACN and water, which one is more easily get evaporated? Which one? Of course, ACN, right? ACN is more easy to get evaporated. So that means that if you have a higher fraction of organic phase, so in the mobile phase, when your sample comes out, so that could a high fraction percentage of this organic solvent, so that could help increase, that will help to increase what? Increase the ESI sensitivity, okay? So this is what going to do. So high fraction of organic portion can do that. Okay, so and I just want to mention a little more about the because we're talking about the liquid chromatography part. Probably I just talking about something extra. So and also for the buffer, there are multiple choices of the buffer. You see, sometimes formic acid, sometimes using acetic acid, sometimes even using like phosphate buffer. I think most of you guys quite familiar with phosphate buffer because you use that a lot when you're using the UV detector. If you're using say LC UV visible detector, the DAD, okay? So the most popular when you're using the LC UV detector, when you're using the UV detector, the most popular one are phosphate. So phosphate is often used. So when we're using the phosphate buffer, this one. So additive for that one. So it's pretty used, and also the acetate, sorry. The acetate buffer is often used as well. So the phosphate buffer has multiple one. So because it depends on how many hydrogens do you have it, right? Because we know phosphoric acid H3PO4, right? So it has 3 pKa value. So here also, so it has different range. If we have like say 2 hydrogen there, so it can be the pH 1.23, and then so if we have the 2, just so 2 and 8.2, and then so we have this one pH is 13.3 and 11.3. So the phosphate buffer has 3 ranges. For acid buffer, so it has the range of say so 3.8 minus pH and 5.8. Okay, so pH is 3.8 to 5.8. So for UV visible, the phosphate buffer and also the acid buffer is more popular. But remember, if you're using a silica-based column, as you mentioned, so it has a pH range. So pH range should be 2 to 8 normally. So because when the pH below 2, we know the silica bond that the base the column is not stable. If it's higher than 8, it's not stable either. Okay, so its back bond may just solubilize. Okay, so but however, if you're using, we're talking about buffer, but however, if you're using the LC-MS, okay, so and then the buffer need to be the buffer need to be the acid need to be the buffer need to be volatile. Okay, need to be volatile. And then so there, then phosphate. Not good. Okay, because it's not really volatile. The phosphate, do not use phosphate buffer for mass spectrometer when you're using the LC-MS ESI. So what we normally do, so that you can see, we're using formic acid. Can we say 0.1% formic acid? So the pH is around 2.7. So and then so what you can also use is so formic acid can be one. Okay, so the other one can be something like say ammonium formate. So the formate can be okay? And then can be the ammonium acetate. So they're good choices because they are small, volatile, and also so they can be easy, actually also can be soluble in higher portion or higher percentage of organic solvent. Okay, so just pay attention. So when you're using a buffer or acidic buffer, so it depends on your detector. So especially phosphate, which often widely used for most popular use in UV, is not suitable for the mass spectrometer. Okay, so and that's what we want to mention a little more. And now you can see this is for example, and then so this is what you're monitoring, and then so you can see it shows very sensitive, really nice peaks in so 8.1, and this one so leucometal concrete is 13.2. So we monitor the most abundant one, right, for quantification. The other one for confirmation. Okay, so let's see. Probably still like mention a little bit about this one, and then so then that's this all for the reverse phase chromatography and null phase chromatography, and then so there's some special type of partition chromatography as well. So we're really talking about the normal one. So reasonable one now, but there's some of the special type. So one of the that you may see often is reverse phase ion pair chromatography. So and why? What is that? Why we have to do something like so troublesome to do, let's say, ion pair? Okay, so reverse phase, this one ion pair chromatography is in order to increase retention of some ionic or ionizable species in bounded phase. So and you can see here. So this is the counter ion. This is one to bind. For example, if you want to analyze so chloride ion on this one, so this iodine, so carboxylic acid iodine, so using the C18 column, obviously not a good choice. But however, if you have a counter ion, so which can kind of like say neutralize this charge and then have a so nonpolar or hydrophobic tail, and then so that the new formed species, the ion paired comp species, can be suitable for the C18 analysis, right? C18 separation. And again, for this one, so now if your target is like a metal ion, so they're not really suitable for C18 separation. But however, if you have the ion pair reagent to add a hydrophobic tail of it, so that can make it. Okay, so probably see this mechanism first. So there are two mechanisms proposed for this ion pairing partition chromatography. So the first one, the counter ion forms an uncharged ion pair with a solute ion of opposite charge in the mobile phase. And then this ion pair then partition into the nonpolar stationary phase, give different retention of the solute. So based on the affinity of the ion pair for these two phases, like so here is like say, this is your solute ion, this is target, and then so you have the ion pairing reagent, so reacted in the mobile phase, and then so this ion pair altogether partition, they have this hydrophobic tail now can retained by C18, for example. So this is one. So the second mechanism is what? So the second mechanism, you can see the counter ion now already retained, so strongly by the normally neutral stationary phase. And then so the counter ion already, the hydrophobic, it has hydrophobic tail already bounded to here. It has its ionic head pointing outside. So it has seems like it has a second layer of the stationary phase. Now it has make them to be a pseudo strong ion, not strong, ion exchanger, right? Okay, because now the stationary phase become charged in this way to positive charge, so it can retain ion. Okay, so and this one is saying they bound first strongly to the station phase, and then cause a charge to this surface, and then the separation just happen. So you see this one. So that's why. So when we talk about the rotation of this one of the compound, so it really depends on the hydrophobicity, how hydrophobic is the ion pair reagent, because normally it has a tail, right? So this part, it has hydrophobic tail. So here, hydrophobic tail, okay? So depends on hydrophobics of the ion pair reagent and analyte as well. So there's a variable factors that can influence the solute retention for this reverse phase ion pairing chromatography. So, and of course, it has the type of content ion. So, and if it's like, say, the better ability to ion pair and the longer retention, of course, right? So it has the more, that means that more of the analyte has been ion paired, and then have a hydrophobic tail, and then can be well retained. And also the size of counter ion. So the larger size of counter ion, the larger hydrophobic tail, and then more non-polar and better retention. That is also true. And also concentration of the counter ion, of course, more of them, and then so more, so and more efficient. So those ionic solutes, they become converted to be this counter, so ion paired new compound, and then have better retention. pH, the effect, it really depends so on nature. So so if the pH maximize concentration of ionic form, so that can increase retention, because then like say 100%, then ionic 100%, so available to form this ion pair, so the new product compound, right, can be retained. And also the lipophobicity of organic, that means when the organic solvent, the mobile phase, become less polar, and then so the K value so will decrease, right, because it's more strong elution power to elute those non-polar so ion pair species out. And then so also this one, so I think I don't need to say one by one, it's just common sense using the knowledge you have so far, so it's easy to understand. So why have those kind of effects? It's just for information, because it's this technique, however, we say that is so clumsy, right? So because this technique, you can see is just using you have to add so the reagent, right? So and then so you have some reaction going on here. So obviously you can see that this one, so and normally the reagents, they are harmful to the silicon. And then so you have to make sure the pH is good. You have to good control pH. So this one so may not be good. And also you have to control pH, because we see that pH can influence the result as well, right? Okay. And also the equilibrium of this ion pair system is quite slow. So, and if you need to change your mobile phase, and then so you have to pump at least 20 column volumes, so this is really time consuming. And then so also the ion pairing equilibrium are temperature dependent, okay? So as you can see, so when temperature increase, retention decrease, and then you have to really control temperature, and also reaction going on inside mobile phase is, let's say, not really good. So really, it can make the overall analysis time much longer. Okay, so and that's why it's not really so popular. It's not really something like, say, people really want to use. So and then, but there's another type of the partition chromatography, which is called the hydrophilic interaction liquid chromatography. So and this one, what is that? HILIC. I guess you guys may have heard that before, right? Hydrophilic interaction liquid chromatography. You see, hydrophilic, from the name, we already know that. It's dealing with those compounds, more hydrophilic. That means more polar, right? Okay, so because we see in reverse phase, the column SC18C8, they're not less polar than mobile phase. So, and then so that's not good to retain those polar ionic compound. Okay, so because they just elute near the dead volume. So and then so they need to be derivatized, or ion pair reagent have to induce the retention, but we know it's so terrible to using M pairing. It's not really good one. So that's why people think about using and develop another technique. So Helix, this one is a technique that designed for retention and separation of very polar and ionic compound. Very polar and ionic. Okay, you can see, and it's again using some standard organosiliconization chemistry to modify the surface, the same as what we do for reverse phase or normal phase. They have reaction going on, so it has this like tail for the functional group. And then depends on what the R is. So if the R group on this organosilane reagent, so it has a polar functional group such as cyano, amino, diol, this one, then so the material has the ability to retain certain hydrophilic compound. You said, yeah, you mentioned that. That is normal phase chromatography. You already mentioned that. So what is, so then I know the normal phase can do that. So why not just using normal phase chromatography? Why you have to think about some hydrophilic interaction chromatography? What is that? The normal phase chromatography is more polar stationary phase. It should be able to retain more polar species. Why bother? Okay, good question. So think about the mobile phase. Think about the mobile phase, okay, of the normal phase. What are they? What are they? Do you still remember that triangle selectivity? And we mentioned several ones, right? What are they? They are hexane plus methylene chloride, hexane plus azer, and so on, right? Okay, so hexane or methylene chloride, DCM, so are they, when you're using LC nowadays, you're normally using LCMS, right? So do you think like hexane, so this kind of solvent is good solvent for ESI mass spectrometer? Is it? Is it hexane? Yes or no? Obviously, no, right? Okay, so they're not really polar, so they're pretty non-polar. So, and then they're not really a good solvent to be used also and it's in the mass spectrometer. Okay, so it's not really easily, they cannot be easily ionized in ESI. So not really a good choice. Okay, so, and because of that, and that is part of the reason. So, and then, so, and also because like I said, people also want to think of using like not just polar neutral compound, they want to deal with some ionic species as well. So, and then so let's make the development of the Helix hydrophilic interaction in chromatography. So the functional group R is hydrophilic and quite often even charged. So, and then if it has the, it can be negative charge, positive charge, or just a neutral triple ionic stationary phase. That means the, so and both positive and negative they put together and then to be neutral ionic. Okay, so probably how about, so because I have to stop early today, so how about we say stop here. So and then so as I mentioned, because I really have to take care of the small one. So and then so we're going to continue like from this slide. So next week. So and we also are going to talk about the UPLC part. I'm going to upload some remaining notes, like say ion chromatography and that one onto the BU e-learning as well. So see what our progress is. Okay. So so that's all for today. If you don't have any questions, so I'll probably stop here today. Okay. So that's all. Bye.